All right, so we are beginning part 3. So to build multiprocessors, we assume we have uniprocessor components, processor, memory, I/O components, what have you, but we need other things to put them together in a cohesive manner. And we dealt with perhaps the most important component for the last couple of weeks, what I call the shared memory substrate, the coherence, and we learned that it turns out it's not just cache coherence, memory consistency becomes an issue, so we dealt with that. Now we're going to move on to some other primitive that the hardware needs to provide to make the concurrency more manageable. So I call that the coordination of concurrency, and it used to be called synchronization mechanisms, but then there is also transactional memory that is a relatively new topic, and we'll see about that. The problem of the need for mutual exclusion has been explained early on, but I'll just go over here one more time, where we have, let's say, a huge array that we need to go through and sum up, and in an example where we break this down to 2 processors, each going through its own little loop to do the partial summation. And the reason we use different variables here and here is so that this part is completely parallelized. Now, of course, if you still remember the notion of false sharing, you would see that if we simply put them in the same array, we might suffer from a big problem of false sharing. But conceptually, it will work fine, and practically, the performance may suffer, but the correctness is not impacted. So when we're done with the partial summing, we need to consolidate that to the global sum. Despite all this discussion about right atomicity, sequential consistency, even with the strongest guarantee of atomicity, we were talking about atomicity of an instruction, not a statement. Okay, so statement like that, although it's very tempting to think about it as one entity, it happens or it didn't. If you're just a pure software programmer who didn't care about the underlying machine, you'd like to think this is, quote, one step. But as you can see, it can be decomposed into a whole bunch of instructions, and really what matters are the memory instructions, the loads and the stores. And in this particular case, we can see that this is a perfectly possible interleaving, with this happening, followed by that, perhaps followed by that, with the last being this one. And if you go through this, you can see clearly only this side of the instructions actually carried out effect to the global sum, right? And now you see why we really need the hardware to give us a mechanism to say, to express that we need this to be done atomically. Atomically, again, nothing is really atomic. They always take a finite amount of time. It's not 0, okay? So it's atomic with respect, always with respect to another relevant set of transactions, set of memory accesses or instructions. So to allow us to do that, we have the notion of critical section. And the notion is, in the critical section, at any single moment, only one thread is executing inside the critical section. Everybody else is outside. And that's the need for this mutual exclusion. Only one thread can be in that critical section. Okay? So this is going to involve a whole bunch of sections in the textbook. If you go with the Dubois textbook, it's mostly chapter 7.5 in the coherent thing. It's sort of spread out into 2 different places because, again, the topic was separated into the bus-based system and the more distributed system. So we will learn that there are some basic concepts. We call them logs for the mutual exclusion guarantee, but there are other synchronization variables or mechanisms, flags, barriers. And then what we want to know, what we will move on to discuss, is kind of a notion that we don't like these logs. We'll see why. And a new way of doing this, a whole bunch of new ways of doing this have been proposed, and they're generally called log-free algorithms, but there are different shades of guarantees. So we'll take a little look into this, not a lot. We have a couple of seminal papers on this, again on the website, on Blackboard. And this drives us to understand what sort of hardware primitives we want to provide. We can use this to support these basic primitives, but we can also provide something else. Okay? For instance, transactional memory. We'll do a very, very brief whirlwind tour of the concept. It's very, very messy, unnecessarily so, but that's, it's a topic being discussed. So a lot of concepts are being proposed, making, in my opinion, a lot of the same mistakes that was made in creating all these memory consistency models. We'll see about that. So we will touch upon some scalable algorithm. If you're building scalable coherence, scalable multiprocessors, there will need to be this support for scalability in terms of the synchronization primitives. We'll discuss that. So we're going to focus on the practical, the common ways of dealing with things. I do want to touch on one thing, and that's Decker algorithm. And this is an algorithm that, as far as I can tell, we don't need any hardware support. It's not very efficient necessarily. It may not be practical, but so that you know that this has been proposed in the past. The idea is rather straightforward. The code looks something like this. This is more of a Pascal kind of syntax where assignment is semicolon and equal, and equality test is equal. I just took the code somewhere and I oversimplified it a little bit here to show you the idea. So we use flag to indicate whether we want to go into a critical section. Okay? And the flag is divided into these two different variables, one for each processor. So P0 will set its copy, and if I want to go into the critical section, I assert the flag to say I won't. But before I am allowed to go into the critical section, I check my counterpart's flag. And if it's true, then I'm going to wait. This is an empty spin loop. I will wait until it's reset. So flag 1 equals false. That's when I enter into the critical section, and when I am done, I will set my flag to false. Okay, so basically I'm reading only one variable and I'm setting another variable, and I don't need any other mechanism to help me guarantee mutual exclusion. So pause the video now and try to answer the question, does this work? Is there a problem with it? So you might remember, I explained this. So the very first thing you want to test is to see if you have deadlocks, and that's sort of the case here. Imagine both processors, or both processes maybe, want to enter the critical section at the same time. So in cycle 1, both of them would assert their flag. And in cycle 2, they would go on to read the other flag. and both detecting the other's intention to go into the critical section, and therefore waiting indefinitely. And that's a deadlock. Okay? So this is bad. It doesn't work. So the real code is slightly more, I need to get rid of that. The real code is slightly more complicated. There is a turn signal. Okay, and so you would go through more rigorous test of the situation to avoid any deadlock. But the key idea is here. This is perhaps the basic idea. So it works to guarantee mutual exclusion. Perhaps it's possible to extend this into more than one. Into the case of more than one, having trees, whatnot. This is not being used as far as I can tell. So the general approach that we've been using has always been something that contains three components: an acquire, which asks for the permission to do something, to enter a critical section, to proceed past barrier. It's very common. Say, can we do this? Right? Are we allowed to? That's the coordination part. And once you are allowed, you would go on and proceed past the barrier or enter the critical section. But if you are not allowed, the conditions are not met, you would then wait. There are two ways of waiting. You can spin on a loop, or you can even yield the processor by going to sleep, putting the thread to sleep. So the processor is going to pick up another thread or process to continue. So the acquire has to have the side effect that if you're applying the permission and you are allowed to get the permission, very often you need to have the side effect to deny at the same time the same permission to other acquirers in the future. So this is the atomicity requirement. So we will see how this is done. Okay, so it's really mostly the acquire side of the things. The release side, to say that I'm done, I am out of the critical section, is usually almost trivial. It's simply to, since you're in the critical section, you're the only one who can give the permission. It's a simple update to a variable to indicate that another thread is allowed to proceed. Okay. How do you implement something like that? Well, you can have hardware solutions, complete hardware solutions. Still remember the bus-based processor, when they want to access the bus, what do we do? Well, right? In fact, what we didn't show is their individual wires, maybe just to use a different color, individual wires coming out of each processor. Okay, to indicate the desire to access the bus, and you have an arbiter. And of course, the arbiter would communicate the decision back, potentially back with using the same wire, but usually perhaps a different pair of wires, a different wire in the same pair to indicate the decision. So that's arbiter. And this is basically deciding mutual exclusive activity or access to bus. You can obviously do the same thing for lock, but it's inflexible. Okay? The bus, we know there is only one. There's only these many nodes trying to access the bus for this particular machine. That's done. For software coordination, you may have different software locks going on at the same time. So a hardwired version is unlikely to be efficient. So the popular approach is the software, the hardware, or the system will provide you primitives. Most likely an atomic operation. For instance, test and set, this would be an instruction. It could also come in the flavor of compare and swap. Okay? So a test and set would be, let's say, this instruction. Okay? It would test a register, a memory location, let's say X. Okay? You're loaded into R1, so you can decide whether it's 0 or not. but at the same time, you're setting x to 1. Okay, compare and swap would be slightly different, but pretty much the same idea. So let's say it's compare and swap R1 and X. What you would do is to exchange the content between the memory location and the register. So whatever is in R1 goes into X, and then whatever is in X comes into R1. Then you can check to see if the value is 0, and so on. This is the primitive. It's an instruction. You can execute it. It has certain features, but it's not a log yet. Okay? The software needs to implement the log. So this is how it looks like. Let's use the example of a test and set. I would provide these two library calls, okay? Log, unlog. And it's fairly simple. The most straightforward implementation is fairly simple. What do? I have a register. So you will call, this is a function call, so we have a return over here. You would call log, and perhaps to pass on the parameter with the location of your software log. And we're going to do a test and set using a register. So the result is going to be loaded into the register, but the memory location is going to be set to 1 after this instruction. So if it hasn't been logged before our try, then the register is going to be 0. And then if it's 0, then we're done. If it's not 0, branch. If not 0, we're just going to branch back and keep on testing it. Okay, and we will be done when the log, when location is being set to 0. And who's going to do that? It's the unlock. Whoever is in the critical section at the moment, we will unlock it when it's done, and that simply involves setting the location to 0. Okay, done. We have now the hardware primitive, in this case a instruction, then an atomic instruction. The loading and the setting of the memory location is done atomically. And again, that's with respect to another effort. Okay, it may take 25 cycles, but during the 25 cycles, that memory location is not going to be written to by another attempt. Now, let's pause a little bit just here. Look at the code, okay? You know how it works now. Tell me if this is good. Really think again. Is it good? If not, what's the problem? Well, the issue is fairly simple. It's terrible. It's not just not good, it's really the worst you can get. What is a test and set? It's a load and a store combined together. So whatever you have to do for those operations individually, you have to do them for the combined operation. So what do you have to do when you write to a memory location? By now you should know. Invalidations. If it's a cache invalidation-based coherence protocol that we're implementing. Now imagine this. I have a whole bunch of threads running. They each run on a processor. Let's just say on a bus-based processor, bus-based model processor. Okay, and this guy is in the critical section, so he's working. And the other threads, unfortunately, are waiting for the critical section. They're executing this loop. What do you think happens? The test will fail. So they will keep on looping back. And what's the effect of that? The effect of that is they're going to grab the bus, invalidate everybody. Grab the bus, invalidate everybody. Okay, so, and that's going to be back to back. Look at my code. It's very tight. It didn't have any breathing space. So, if it used to take the critical section 10 bus cycles to finish whatever is needed in the critical section, now the thing is just going to be that much worse. Why? because now you're competing with these guys who are waiting for you, but they're noisily waiting for you. They're broadcasting, they're basically taking the bus away from you unnecessarily. Let's say you're preparing dinner for your friend, and they come in, they stop you, they ask a question, is dinner ready? And you have to stop what you're doing, talk to them and say, no, and then they will go back, come back again, and ask you the same question, okay? For all fairness, the arbiter is going to say, well, this guy has just done something, so it's this guy's turn. And then it's this guy's turn before you're allowed to proceed. So you don't get a whole lot of bus bandwidth, okay? And this is obviously terrible. You generate back-to-back requests for nothing. You're not doing anything useful. And it's in fact in your interest to shut up, to not bother the thread that is, or to not take away resources that could help the thread in the critical section to finish what it's supposed to do, in order to give you the chance of entering the critical section. Okay? So just to think about how bad it can be, let's do an experiment. The experiment is very simple. We write a piece of code that doesn't do anything interesting at all. It issues a log request, and it then enters into a fake critical section which doesn't do much. It basically waits for a variable amount of time before unlocking. So C is the variable. C could be 0 to say, okay, nothing, I'm doing nothing. Or it could be a number to say, let's wait for this many cycles, or whatever is the unit. All of this was done, and it's the example from textbook, was done on a very old machine. The bus is very slow, it takes a microsecond on this SGI challenge, but the point is exactly the same, okay? So I guess I forget to say that, to ask you the question, how you would solve the problem. Now, there might be many ways you're thinking about solving the problem. Good time, pause the video, write down what you think is a good solution. But here I'm just going to explain one solution, one mitigation. It's not even a solution. The mitigation is this: back off, okay? If you failed, you tried, don't go back and try immediately. The chance of that happening, of you getting the permission the next cycle, is not very high. Why don't you back off a little bit? Wait, take a stroll. Wait for a couple of cycles. And the more you try and fail, the more you should back off. Why? Because you know this is very, you come to the post office, there are 2,000 people, or you tried, you couldn't mail your package. Now you can say, okay, let's come back much later, this afternoon, tomorrow. And the typical solution for that is an exponential back off. You may start with some cycle 2, and if you fail, you increase this by, let's say you double. Okay, so that's basically multiplying by a base, in this case 2, raised to a power of trial. And so this is a common thing, and in fact we did something similar in a different setting. We were questioning what is the most optimal back-off algorithm. We didn't find any systematic treatment of the subject, but people seem to always do exponential back-off, so we kind of did a very cursory experimental analysis to say, okay, fine, let's assume that's how you back off, and let's sweep the design space a little bit to see what K and B value to use, because the B that we saw was just 2. That sounds to me like just an intuitive guess rather than. So in our situation, we tried this. Long story short, our best base turns out to be something very small, I believe it's 1.1, if not smaller than that. So you can see it's at that kind of a small base, exponential backoff is about the same effect as a linear backoff. Okay, so backoff, the concept is what's useful here, not the exact magnitude. So let's guess. Okay, here I'm doing a whole bunch of experiments, changing the number of processors running this thing, and measure the time per critical section that I managed to accomplish. Okay, so what do you think? Well, ideally, this is a critical section, meaning at any point, only one thread is making forward progress. One thread is scoring goals. Okay, so no matter how many processors, the number is going to be flat. Ideally, it's not going to improve. It's not going to go down, you know, like that. Okay, again, it's critical section. So, question is, what do you think happens if I don't back off and I use this really stupid, simple test and set procedure? And what happens if I do back off? Again, pause the video, draw on your sheet of paper. What does it look like? Is it going to be like that? Is it going to be like that? What happens? So here is what really happened. I hope you pause the video. Now, it's a little bit off. I don't know why these are really supposed to be triangles and whatnot, but okay. The top line over here, as you can see, this is time. So the higher, the worse. The top line over here was basically the code that we just showed. So it's pretty bad. And you can see it goes up almost linearly. So the more helper you have, the worse it is. And that makes sense because these are not helpers. They're just disturbing influences. Okay? And having a back off does help. Although it didn't, in the particular implementation, it didn't really seem to change the exact trajectory. It's just lower in some way. Okay? It didn't make this flat or anything like that. Sorry about that. But it helps. Okay, and this is again just one experiment. And if the backoff was written on a different place, perhaps the experiment would show slightly different result. So just one small question for you. It's an interesting kind of detective analysis. Why do you think this happens? So what we did is we compared two experiments where one has a critical section of 0 and the other has a critical section of 3.64. By the way, all that we're measuring is just the overhead. Okay, what is the cost to get into the critical section, not the critical section itself? So having a large C is not going to impact the overhead in an intrinsic way. Okay, why? What do you think happens if C is 0? So we go lock and unlock with nothing in between. If your answer is cache coherence, you're on the right track. What happens when C is 0 is that the thread getting the critical section right will immediately issue a write. Okay, and it's possible that the data is still in the cache, and therefore you will be able to do that. But if you have a non-zero critical section, as we can see over here, well, the part that we drew over here, before you will issue any unlock, another thread is likely to have come in and grab the log, not grab the log, but invalidated the location from your cache, so that because they issued this instruction, right? So having a 0 being the critical section length gives you slight advantage there. So you see, what's the point? The point really is having a lousy coordination algorithm can be a very bad performance problem for you, hence the need to discuss these matters to create better synchronization mechanism, which we'll cover in the next video.